welcome back. Thanks for coming and for joining us today. When we go through today's material, it's probably going to be a little faster than the last couple of days. We've got a couple of sessions to do essentially, so there'll be a little bit of extra time to do the homework assignment. Nonetheless, maybe a little bit less time on the preparation. Were there any questions or thoughts about the assignments that you were doing last night or this morning or this afternoon? Was it, I mean, in terms of, bars, shafts, beams, trusses, did you have any revolutionary insights? Okay, that's okay. They're pretty simple structures, and I think we went through the problems pretty thoroughly, actually. Today, we probably won't have a chance to go as in depth in terms of the details of every problem, and these problems are going to be significantly harder than the ones we've been doing up to this point. The methodology, though, everyone now knows if you're looking at doing equilibrium, which is one of the pillars of mechanics, we gotta first think about external loading and do the equilibrium there. And then we did one example, right, where depending on which side you slice, actually it wasn't as big a deal. Okay, but generally you're gonna wanna do external equilibrium first, and then you have method of sections or method of joints. Okay? So today, what we're going to cover is bars, and bars. But we're going to think about them in terms of being springs, and we're also going to think about them in terms of their deflection. So this is now the first time, I believe, we wouldn't have done this in statics, that we say that we can figure out how much a structure is going to deflect. Now, you've done physics, you've done work where you've thought about springs, so you're not foreign to this idea that if I put a load on a mechanical system, I'm going to have deflection. We're going to establish some connections that maybe you haven't thought about prior. So in doing this, and there's some space for notes. If you download, I re-upload the slides this morning or in the last hour actually. So if you want a little bit of extra space for notes, you can re-download and then write on them. But anyway, when you think of springs, these images are probably what come to mind. Now, yesterday we talked about the torsion bar a little bit in the back of your trunk or the back of your vehicle in the trunk, and that's another type of spring. But when we think about linear springs, you're thinking about some type of helical coil. And you probably also recognize that real structures have springiness to them. I remember my sophomore year, and we were going over mass spring dampers, and I got super excited that whenever I sat next to a table or something, if I hit it, I could see it go and then damp out. I was like, yes, second order underdamped system. I'm such a nerd, okay? But you have already probably realized this, maybe not in the context of dynamics, but in terms of statics or in terms of stepping on a bench that deflects, stepping on a wood panel in your floor if it's an old house that deflects, and we're familiar with this phenomenon. What we like to be able to do is leverage what you already know how to do, which is to say, if there's a spring constant, I can relate the force and the deflection through that spring constant. And this is Hooke's law. So sometimes it's written as F equals minus kx, and sometimes it's written as F equals kx, right? Newton's third law at work again. If I'm thinking about a spring that I'm stretching out, oh, look at this. You remember how I drew a little rectangle? Oh, look at this. The cleaning staff are so amazing. They're like, what's up with that? They erased it. Okay, but anyway, so if I stretch this out, I can think of a positive force in this direction that I'm exerting on the spring, right? Or I can think of this pulling force that the spring is exerting. That would be the minus kx version, right? That's pulling against my hand, okay? And it's important to realize that in one case, the force and the displacement are in the same direction. In the other case, the force and the displacement are in the opposite directions, okay? In this class, again, we're going to think more about F equals kx with a positive relationship between the force and the displacement. So here's just a little bit of an illustration that we can have a pull force, and the pull force we'll say is going to be equal to kx, same thing. Now, you probably remember at some point the relationships for springs in parallel and springs in series. Where do you learn this? I'm not actually sure. I remember it, I believe, from my high school physics class, but where do you teach, where do you get taught this information nowadays? Probably dynamics, maybe?
I don't know, but I only really did parallel and series in E&M physics.
Oh, E&M, okay. Well, then maybe this is a new concept for okay, all right. Yeah, so you remember the resistors in parallel and the capacitors in parallel and the springs, or the resistors in series and capacitors in series, okay? So they're actually, the analogies are flipped here if you're thinking about resistors. Remember the resistors, actually, let's see, wait, hold on a second. No. Okay, capacitors and resistors are flipped, all right, in terms of their analogy. Okay, sorry. Okay, brain moment. Okay, but if you have two resistors in series, actually, yeah, they are flipped. Okay, back to my braininess. Okay, right. If I have two resistors in series with each other, right, I can add those resistances up. Okay. Here, okay, if I have two springs in parallel, I add them up. Okay, so maybe you could say that the springs in parallel are more analogous to the capacitors in parallel. Okay, so intuitively, right, if I have, I don't know what I can do here, but if I have, two legs on this table, okay, and I add two more legs that are the same stiffness to this table, I know that it's going to be a stiffer structure, okay? So that's springs in parallel in action. Okay, so when we do that, what do we say? If we had a K1 and a K2, we're going to say that the effective K, or the K parallel, would be K1 plus K2. Okay? And again, it's good to remember, so essentially we have, at this point, two formulas. We have F equals K delta, or F equals Kx. All right, we'll use delta a lot in this class, so it's just another variable, right? And we have now that the K parallel is K1 plus K2. Yeah. And if we have springs in series, this is maybe a little bit less intuitive. But remember, I think 2 days or a day ago, we were talking about a cable hanging from the ceiling. And if I extend the length of that cable, right, if it's a very short cable, well, first off, if it's the same material and the same diameter, both of those cables will support the same amount of load, right? Because remember now that the supportable load on a cable or a bar is related to the cross-sectional area. If, though, I have a longer cable and I pull on it, the amount I'm going to fall is going to be greater, all right? I haven't done the math exactly, but the longer your bungee cord is, if you jump off of a high cliff or something, the more deflection you're going to get once that bungee cord becomes fully extended. So with springs in series, we write them like this. And just like the resistors in parallel, the effective value goes down. Okay? So if you have another expression, 1 over k series is equal to 1 over k1 plus 1 over k2. Okay? And another way to write this is k1, k2 over quantity k1 plus k2. Maybe I should have gone through this derivation. I don't have it here, but if you go to that YouTube video, I guess, that I have the link there, you can see the derivation. And it has to do with the fact that and it's not a very long derivation, but in parallel, both springs experience the same amount of displacement. Okay, so this is a pretty key point. They experience the same amount of displacement, but the amount of force that they could be experiencing might be different. Okay, now if they're the same spring constant and everything, and it's a symmetric loading, then both springs will be experiencing the same amount of force. But the boundary condition essentially is displacement is the same. Maybe I'll just write that here. Okay, so in springs in parallel, we have same displacement. Oh, that looks bad. Okay, but different forces. And in series, what do we have? We have the opposite. We have the same forces in each spring, but different displacements. And of course, that's with the exception of you have the same values for the spring constants. Okay? And this is a powerful concept that you want to remember about extending the length of a structure. If you extend the length of the structure, the force throughout that structure, if it's a bar, okay, more specifically, the force throughout it is going to be the same. But you're going to get additional displacement, and the displacements of different stiffnesses or different regions in that structure that have different stiffnesses is going to be different. Okay, any questions on this? Now, let's make things a little more interesting. We're going to start analyzing these different types of structures where you have different bars in parallel or series with each other in configurations where we're going to assume that these beams here are infinitely stiff for now. Okay, eventually we can handle it not being that way, but you could also start to assign spring constants, okay, to the deflection that you have of these beams, and we'll do that at the very end of the class. At the very end of the class. I think it's the last session that we have together. So let's think about a bar, which we've already been talking about quite a bit, and its deflection. So if I've got a bar with two forces acting on it and it's magically not moving anywhere, I can think of how one end is deflecting relative to the other. And we won't do the exact derivation of this spring constant, but what I'll tell you, and you will be able to do this exact derivation next week, is that if I have a steel bar and it has some diameter and it has some length, I can assign it a spring constant or a coefficient. Okay, some people like to say spring coefficient, some people like to say spring constant, some like to say spring rate, all the same. So if I put a millimeter if I get a millimeter displacement, I get 165 kilonewtons of force. That's a lot of force. That's a lot of force, okay? So the simple bar that you might find lying around that's only a centimeter in diameter and it has 10 centimeters of length, a tenth of a meter in length, that is not going to want to deflect much, okay, relative to your rubber band, for example. So when I draw out an equivalent spring, I don't know, now you can start to think of this in terms of circuits. I can say, okay, here's a bar, it has some K associated with it, and I can say it's a spring, and we can say that maybe I have a new bar that I increase the length to twice its original length. So that means I've now put two springs in series with each other. We just talked about what happens here. So what is the new spring rate? What is the new effective spring rate of this structure? If I have Ki, all right, for one spring, and now I double the length, or sorry, one bar, and I now double the length of that bar, what is the new K? Yes, Andrew.
That value squared over twice that value.
Okay, and then what does that equal?
The series.
Okay, well, you said K squared, right? Ki squared over 2K, which is, just do, you right? You said K squared, right? I like what you're doing it exactly right. And what does this equal to?
K over 2.
K over 2, exactly. Okay? Right? So that's using the formula we just gave you. And again, right? Doubling the length means you're making it twice as springy, or you're decreasing the spring rate by a factor of 2. Okay? So a lot of times we talk about compliance and we talk about stiffness. They're flipped. Okay? If I say something is very compliant, that means it has low stiffness. If I say something is very stiff, it has low compliance. Okay. So it's kind of a good thing to keep in mind. All right. And even more, I don't know, touchy-feely or more of a scaling rule is that as the length would increase, I can relate this. This is an inverse relationship, right? So we talked about scaling with, was that 2 days ago now? Yesterday? I can't even remember. Things are going so fast. But we're talking about, again, a scaling relationship where if I have the initial length and I divide by the new length and I multiply by that K, that's going to give me the effective spring. Okay? Now, what happens if we double the cross-sectional area of the bar? Okay? So now I've got, all right, so what do you all think? I think now, all right, we got a pattern here going, right? So if I double the cross-sectional area of the bar, what does that do to my system? Joshua, you look very pensive. What are you thinking?
Intuitively, should be stronger.
Okay, so very interesting. I like that you use the word stronger. It is actually stronger, okay? Okay, it will be. Strength refers to yielding, right? So how will it break essentially? Okay. We're talking about stiffness right now. So now let's use a different vocabulary. Is it going to be stiffer or is it going to be less stiff? If I double the cross-sectional area of my bar.
Should be stiffer.
Yeah, exactly, right? You said stronger, and now I'm saying we're talking about compliance, we're talking about the deflection, so it's going to be stiffer, right? And if I double it, then how much stiffer is it going to be?
Should double.
Right, not a trick question, okay? So essentially, we can write it out like this, okay? And we now have two springs in parallel with each other, and we can double the stiffness. Now, granted, this looks like a system with two bars in it. When I say double the cross-sectional area, I could just be putting two bars in parallel with each other, or we could be increasing the diameter appropriately. Right now, d squared, right, it comes out by the square root of 2 essentially, right, if I'm going to increase the area by a factor of 2. Okay, so for a new area and an original area, we can also have another scaling rule that we can apply. Okay? And to be honest, these relationships may not be super useful on some of the exams, but the concept is powerful. And so when you start looking at the different systems, oh, I've put another spring in parallel with this system, which you'll see in a little bit, and that type of thing is fair game. Should the stiffness go up or should it go down? It should go up, right? I put another spring in series with this system. Is the stiffness going to go up? It's going to go down? It's going to go down, right? Okay, so let's say that we hang a 2,700 pound roadster or small sedan from the bar shown. Now, would you really do this? Probably not, but the people in the garage that are jacking your car up, they might have a post or a hollow tube that's been pressurized hydraulically to support your vehicle, okay? And let's say that we're using that nice 10 centimeter long, 1 centimeter diameter bar, cylindrical bar, and there's the roadster hanging very poorly by my crummy drawing. So, or there's the sedan, okay, hanging by my very crummy drawing. So, going back to this equation, F equals K delta. When we write, we say that delta, if we want to know the deflection, sorry, I probably said that. If we want to know the deflection, we can just say the deflection delta is equal to the force divided by the spring constant. Keeping track of the units, very important, okay, that we do that, because we had units in pounds and we have a spring constant in newtons per meter. Kilonewtons per millimeter, all right, that you multiply by 10 to the 6, by the way. So when you look at the collab scripts associated with this, you're going to see a lot of times 10 to the 6, because sometimes when you're doing the calculations, it's easier to think of it in terms of newtons per meter instead of kilonewtons per millimeter. Anyway, the deflection is only 0.073 millimeters. That's pretty small. How small? Anyone have an idea? What is 0.073 millimeters, or what is 75 microns? A piece of hair. Okay, so you're only going to get a deflection that's the width of that piece of hair for that bar. And that's pretty incredible when you think about how much elasticity, okay? I didn't use the word strength. I mean, it's incredible the strength that steel has as well, but the amount of elasticity, which then transfers over to stiffness of steel, is remarkable, especially for how cheap it is. And so you can think back now to the Industrial Revolution and how big a deal it was when Bessemer was able to start creating massive quantities of steel, and how they were able to put it into so many different things, from structures to machines. Okay, so if we have time, we'll come back to the assignment questions. What about this type of system? Now, let's change. Now, we just talked about a bar. How do we think about a network of bars? What would be the first thing that you would do here? If you're working on this problem, what would be the first thing? What do you think you would do? How do you approach this problem? Yes, Matt.
Find all the K parallels.
Okay, yeah. So okay, good. So you're going to like try to figure out the K parallel. All right. Which K parallel are you looking at in particular? Which one would you start with?
K1.
Yeah, the K1s on the upper left, right? Okay, good. Right. So I agree with you 100%. And before you even do that, I know it may sound kind of silly-willy, but I would draw a drawing. Okay? So go ahead and make yourself a little network, okay, with the springs. And when you do that, okay, I mean, it was already obvious, right, to many of us, I guess, that K1 and K1 are going to be linked in parallel with each other. But it should then be extremely obvious once you've drawn this diagram. Okay, but maybe it's not so obvious. Like, hey, wait, these guys are in parallel, and this is in series. So you want to try to work systematically through these types of problems and taking down or combining, creating effective spring constants for things that are the simple parallel systems or the simple series systems that can then combine. So what you would probably do, what's the next thing? Let's go ahead and do what Matt and some of you were already saying, and that is write out that we can combine the K1 and K1 here, so now that's a 2K1, okay, and then draw the diagram again. Again, some of you will skip this step and probably get it right. Others of us will skip this step and probably get it wrong, all right? But now you can see, so what's the next thing that you do here? Someone else. What's the next thing I should combine? Yeah.
You could combine the springs on the left in series.
Right, so I would go ahead, yes, exactly. So combine these two, okay? And to do that, all right, I do K1, K2 over K1 plus K2, all right? So that means that now I calculate out the 2/3 K1 for that left branch. Okay, and now, okay, I won't even ask the question because I think people are bored, but we're going to put these in parallel with each other. Okay, and then after I've got an effective spring constant there, then I have to put these two in series with each other. Okay, and the final result, the equivalent spring constant, will be something like this. Okay. And I guess you can simplify it further if you want, or you can make it look a little neater. Any questions on this? Any thoughts? We're making some assumptions here. Okay, and one of the assumptions that we're making is that these things are symmetric. Okay, for example. All right, and we'll cut into the issues with this in a minute. Okay, and we're making sure that those are symmetric too, and it's drawn that way. We're also, of course, assuming that the beams, like we said earlier, they don't contribute any springiness, so they don't deflect either. This may be the time where you want to use Collat, or it may be the time when you want to use Desmos. I'm not ignorant, okay? So whatever floats your boat, because these problems, you're going to work them out, and if you do it on the calculator, that's fine if you get it right the first time. But as you know, and I don't know if anyone can teach me how to do it in Canvas, because there's no penalty if you get it wrong, right? But you just have to keep getting it right, as you know by now. And it just gives you a different set of numbers every time. Okay, and it's annoying. I understand. Okay, but if you use some type of calculator where you can just put in the new numbers, it may be simpler. Okay, collab is one option. There are other options out there. Okay. But anyway, so here you have the different k values that you put together, and then you have a k equivalent, which is the format they have. And you don't even have to make it all fancy like this, right? Once you've gotten this, you can just type print k equiv, kq, right? And then it spits it out. But for us, for just looking really nice and clean, right, I have text. Okay. It's a very nice calculator. It really is. But I understand there are other options out there. Okay. Now, one of the homework assignments will be to look at this system. I think you've got the idea now. All right, what you got to do. We're going to take those in parallel, take these in parallel. Then you're going to have three things in series. Right, and you can use the 1 over k equivalent is equal to 1 over k1 plus 1 over k2 plus 1 over k2. Okay. Or you can go wild and say, hey, I'm going to combine like these two things in series with each other and do like k1, k2 or k1 plus k2. And they're going to do like, oh, I'm going to combine these two things together, another k1, k2 or k1 plus k2. Whatever floats your boat. Okay. But it's also nice if you do it in again, if you're using a calculator, you don't have to simplify it as much, right? You don't have to get it to the nice algebraic expression. You could just be like, all right, 4k1, 2k2, k1, and then I'm going to do like 1 over the k equivalent, right? So k equivalent is 1 over big mess, that big mess being 4k1, the 2k2s, or the 1 over that, sorry, the 1 over the 4k1, the 1 over 2k2, and the 1 over the k, another k1. All right, good. Okay, now, these problems are tricky. What are we looking at now? Okay, it looks remarkably similar, but now this bar is a little bit offset. And even though this bar is infinitely stiff, this lower horizontal bar, we're going to say that it can rotate. Okay? How's the rotation coming into this system? Well, there's nothing to say that. Well, first we have now this thing off center, but after that, there's nothing to say that the force in this leg is going to be the same as the force in this leg. Right? So you have an imbalance in the forces, and this thing can rotate. It's still in static equilibrium, but it can rotate. So for our purposes, in this case, in this example, we're going to do this problem as if the left side is less stiff or more compliant. It's springier on this side. Okay, so imagine like I've got a piece of rubber hanging down here, and I've got like a piece of, aluminum, all right, on the right side. And so it's going to cause it to rock this, it's going to cause it to rotate in this direction, so counterclockwise. And we're going to think about an angle of rotation essentially from either some point out here, okay, that has a theta associated with it. Now, turns out this theta that we're going to use is we're going to also assume it's a very small theta. So in the end, we're going to use a small angle approximation to get rid of the sign, okay, that we have in there. When I say sign, I mean the trigonometric sign, not the plus or minus sign. Okay, so here we go. We start off though, before we do rotation, we make a nice little diagram that's like a network. And now we're going to kind of label these two legs, just 1 and 2. We'll go ahead and do some equilibrium. And for this, you have to maybe a little bit of experience, and I already said it's going to be, we're going to assume small angular displacement. So for this, we're going to say the force balance, okay, on this beam, which is still infinitely stiff, okay, it's going to be like a seesaw. Okay? And so we're going to look at our two forms of equilibrium. We're going to balance the forces, and we're going to balance the moments on this. And for this, we're going to, at least at this stage, we're going to assume it's flat. Because if you have a small angle of deformation, you could introduce slight variations, okay? Like you could say, oh, really I should have like, if it goes this amount, right, that means that if I'm looking at the normal vectors, I've got to introduce other sine or cosine components. But we're going to assume it's flat here for this part, if we're doing the equilibrium, okay? When we do the deformation, of course, we'll use the rotation. So with this, okay, now it's working. I got too far away, I guess. All right, equilibrium of forces. This is straightforward, right? So F1 plus F2 is minus F equals 0. And then, of course, when we do the moments, we better also choose a location. So we know what F is actually, okay, because F is going through this piece right here, and right, the force going through the spring is the same as the force acting on B. So why not eliminate one of our unknowns, right? So let's if we put an A or C, we don't have one of those unknowns there. So now we can write out the relationship between F2 up here and this F. And if we go back to this equation up here, we can write out now a relationship between F1 and F. Okay, so there we go. Just using equilibrium. Maybe that was a little fast, but okay. This is just the exact copy of what we got from the previous. Okay, so we've got the force F1 is related to a ratio of LBC, okay, over this entire length LAC, and F2 is related to LAB, okay, over LAC times the force applied at location B. Okay, now, if this is where things start to get a little bit interesting. Okay, so delta 1, we're going to say is the displacement essentially of A. Okay, it's the displacement in the first leg on the left, one that we call it leg 1. Delta 2, okay, is the displacement in leg 2. And like we said at the beginning, we're going to have the left side being springier than the right side. So when we write this out, what's going to happen? A is going to come down, C is going to come down, but A is going to come down more than C, and that's where the rotation gets introduced. So we can draw it like that. So we have the initial position and the new pose, if you like, because it has position and it has a rotation. So it's like a new configuration if you're doing dynamics or robotics or something of that nature. And so we can say that we have a delta 2 and we have a delta 1. That's how much both of those move. When we go back, okay, to this diagram here, we have that if you have an F1, right, which is this F1 here, we can relate that F1 to the spring constant, okay, of this leg and the delta 1. Similarly, right, we can relate the F2 to the spring constant and the delta 2. Now, here's an angle of rotation. And the length, you see we've drawn a triangle here, a right triangle. And so this triangle from this gray line to A, that displacement we can say is delta 1 minus delta 2. The sine of theta, therefore, will be this delta 1 minus delta 2, quantity delta 1 minus delta 2, over the length of that beam, like you see there. And from this point forward, that's probably the hardest part of the problem, to be honest. Okay? From this point forward, it's plug and chug. So now delta 1 is equal to this expression. Okay? Just rearranging this and substituting this into there, and then we get this. Delta 2 is similarly going to be given by this expression plus this expression. The sine then, right, so now I've got expressions for delta 1 and delta 2, so I can put those into delta 1 and delta 2 here, okay? And they both are multiplied by f, so I bring the f out here, and it's all over LAC. Okay? And even though I said that we're going to say that the left side is springier and rubbery versus like metally or metallic on the right side, now I'm going to tell you that we're going to use a small angle approximation. Okay? You don't have to, okay? But if the stiffnesses are not too dissimilar, even though we've exaggerated them to calculate this rotation, then we can just say that this sine of theta is about equal to theta, and this is an expression for the rotation. Okay? All right. Now, copy and pasting this small angle approximation. It's the same exact thing that was just on the previous slide. Okay, what we have here is, again, this result. Now we can figure out what the rotation is. But what is the total delta? How do we think about that? Well, we draw this again, and we remember that we have a delta 2, right? For C, we have what we can consider to be a delta 3, okay, for this leg, okay, because delta 1 is larger, right, than it's on the left. Delta 3 is going to be less. And so we can think of delta 3 as just this hypotenuse, right, times the sine of theta. And again, we can use a small angle approximation if we want here, right, because we said the theta was small, so you just multiply them against each other. And then delta 4 at this end, right, will be related to, well, that's this. Delta 4 is really just the displacement of this leg. Okay. So now, what do we see? We see that the total displacement, how would you describe the total displacement? From the total displacement, just delta at the end. What do you do here? Yes.
D3 plus D4.
Right, so delta 3, delta 4, I agree, you add those to each other?
Plus D2.
Yes, plus delta 2. Okay, and that's it. Yes.
Which one is delta 4?
Delta 4 is just how much does this spring displace, right? So that's a K3 spring, okay? So that's just simply the force divided by K3. Yes?
Can you explain how you got the total delta?
Yeah.
Why you added them?
Yeah, okay. So we're interested just in the vertical displacement of delta. Okay. Look, C goes down this amount, delta 2. Then B goes down this amount delta 3. And then K3, or this leg 4, if we call it, whatever you want to call it, this stretches by delta 4. So it's just like stepping stones, right? I've stepped, or stairs, right? I've stepped down 1 delta 2, then I go down and step down another delta 3, and then I go down and step another delta 4. Right? So delta 1 was important to us, okay, for calculating out. See you later, no problem. Delta 1 was important to us for being able to do this calculation for the theta. Okay, but now we actually don't need it because it's out here, or it's out here, right? But it's we don't this where we're connected doesn't go down that amount. You got it? Yeah. It's a tricky problem, okay? And I highly suggest. Okay, so anyway, okay, now we actually do the math out here. Okay, and okay, that's all that. Okay, you can plug in some values, right, and you can calculate it out. So yeah, when you're doing, if you really want to just plug this formula in every time, that's great. Or you could just use the collab, okay, that's provided with this session. Okay, again, not forcing you to use it, but just pointing out that all you have to do is change the values up here for the homework assignment, and then it spits it out. Right? It won't be for example 3.3, right? But you just copy and paste it, whatever. I don't even know why I'm mentioning that. But anyway, the value that you get here, right, will be based on all these calculations already done for you. Now, should you be able to do this? Yes. All right. But in terms of making your homework life simple, great. And then over here, this is just showing the symmetric case. So remember we had that similar configuration actually where we had everything kind of symmetrically down the middle and we assumed no rotation. Okay, that's the code for doing that example. Okay. And that's all on the index. Okay. Okay, so this is Q6. Again, the problems are a little bit out of order. Okay, so please forgive me for that. Superposition. Okay, this is fun. Changing themes. The superposition principle, also known as superposition property, states that for all linear systems, the net response testing 2 or more stimuli is the sum of the responses that would have been caused by each stimulus individually. So that if input A produces response X, and input B produces response Y, then input A plus B produces response X plus Y. Okay, where have you seen the superposition principle previously? I actually don't know. but where have you seen it previously? Have you been introduced to this before? Okay, can you remember where? I mean, it's intuitive, right? But where? Was there a class, or was it just in the game of life? Yeah?
Charges for E&M physics, and it was also a little bit in statics.
Ah, yes, good. Yes, that's absolutely correct. Okay, so yes, superposition definitely. You say, oh, hey, I got a charge over here. I got a charge over here. And then I put a charge over here. All right, what's the net force on whatever this original charge, right? The network. Good. Okay, good. Thank you. Forgot about that. And then, yes, good. In statics, you should have seen it as well.
Is this kind of like all of vector math?
Yeah. So this is linear algebra, right? Vector math, right? Whatever you want, vector calculus, linear algebra, linear system. We take big time advantage of this. If I gain 50 pounds because I whatever, right, whatever happens, sickness or whatever it is, right? I'm going to deflect the floor underneath me by, I guess I won't say what percent, but by a significant percentage. Okay, that's the position. So here we go. If I've got a bar, apply F1, I get delta 1. If I have another bar, I apply F2, I get delta 2. If I apply F1 plus F2, I get delta 1 plus delta 2. Okay, pretty straightforward. Now, we're going to have some fun though with this. This is not as straightforward. Okay. Now, to be clear here, because maybe my drawing is not F2, these black forces are actually external forces, okay, that are being applied to the system. So you've got this bar here, and imagine that like I have a hook on there and I'm tugging on it, okay, in those directions, externally. What are some strategies? Well, we just talked about superposition. So how would you use superposition to figure out what the overall displacement is? What do you think? Alexis, any ideas? What do you think, Alexis?
I'm not sure.
Not sure? Okay, that's fine. You haven't seen it before, so it's a little bit new. Anyone else? Yes, Joshua.
Can we do the displacements individually, like for each force?
Yeah, exactly, right? So I can write this diagram 3 times, and each time I write it, I can say I'm only going to apply one force. All right, so I have the whole diagram in once where I have F1 on it, the whole diagram in once where I have F2 on it, the whole diagram I have F3 on it. Okay. So let's get started. Here's our first diagram with F1 being applied to it. Okay. And where are we interested about thinking about displacement? Well, displacement was at the end. Okay? So we want to make sure that we use displacement at the end again. Okay? Now here's a fun thing. Here's a fun fact. Or, this is cool to think about. You're like, well, I haven't quite seen this before. What is delta 1? Or, more interesting, how do I go about calculating it? So I'll take either an explanation of how I calculate it, or I'll take a straight up algebraic response. Yes?
It would just be F1 over K1.
Yes, that's right. Okay, why is that the case?
Looks long.
Hooke's law. Okay, good. Okay, I want a little bit more depth here, okay? When I say depth, I'm actually asking you to think about what the bar is feeling. Okay, we're getting emotionally attached. Okay. Go ahead. Yeah. Okay, now you want to explain?
I think it's just a general idea of I'm trying to break it down with the units. So for each specific area on the bar, it's going to experience a certain amount of force, and depending on the thickness. It's like meters per meter. I'm trying to break it down by the units.
Okay.
I don't know how to put it into words.
Okay, that's okay. So you got the right answer, all right, and you got the right thought. Okay. Let's think about a couple of things. First, what is the internal force in the green region? Well, it's just F1, right? If that's all it is. Okay. What are the internal forces in the orange and the purple regions? 0, right, Dylan? They are 0, okay? So the green region is feeling it. It's feeling it. It's emotionally attached to this force, okay? The purple and the green, or the purple and the orange, okay, are along for the ride, as we like to say, as I like to say, Okay, they're just coasting around. They're just coasting. So whatever displacement I have here, orange and purple will go with it, but they're experiencing no force. Okay? At least just because of this force that we've applied, F1. Okay? So one important realization here is that displacement is, if you think about it, or deformation, okay, is really dependent on what the internal force is. Okay? And that internal force is the same across that green region. Okay? But instead of just thinking about the external forces, we actually have to start digging deep emotionally with these bars and thinking about what's going on inside of them. So, delta 1, I agree, is just F1 over K1. And now things will probably be a little bit simpler, right, as we go to the contribution for F2. Because now we're starting to think, what is the bar feeling? Become the bar. Okay? So now, here, what is, or how do I think about figuring out delta 2? Yes, Dylan.
So it would be as if the first two bars are like one spring.
Good. Good. All right. So they're one spring, and what would their springiness be?
Would be K1 times K2 over K1 plus K2.
Exactly. All right. Okay. So good. So now you've got the answer, right? We've got very close to the answer, right? You've got a force F2, and you have a spring constant, right? So then we can say that F over K2 is going to be delta. That's good. What is the force internally that green and orange are experiencing? What are they feeling?
Compression.
Okay, they're definitely feeling compression, and quantitatively,
Negative displacement.
okay, they are experiencing displacement to the left. Okay, they're feeling though a force. And remember, these are springs in series, right? You just use the series equation. So what we said, right, at the beginning of class, the force is going to be the same in both of these springs because they're in series with each other. So the internal forces are going to be just F2, okay? And they're going to be in compression. So again, if we look at what's in the green, we look at what's in the orange, we can see, and maybe it's good to think about this. Okay, I jumped a couple steps, right? If I do external equilibrium here, right, then the wall has to be giving F2 back, right? So then when I draw the green and I slice it, these are slices, believe it or not. Okay, F2 is on this side, and F2 has to be what's inside it. That's the internal compressive force. Here, right, if I break this one, I've only got F2, right, acting here, so I break it, and so F2 is there, and then internally it's F2 as well. Look, F2s, they're all going in different directions, right? But they're all pushing inside on their elements, which means they're all compressive. Okay? And then the purple, again, is just along for the ride. Okay? There's no internal force in the purple. Okay? But if this moves to the left, this is going to move to the left. Yes?
Why is purple ignored? Isn't it like being pulled? It's because it's not attached to the wall.
Exactly. There's no constraint on this side.
Okay.
Right? So if I take a slice, remember what we did yesterday, right? I take a slice, which I just did, there's no force on this end, so there's gotta be no force on that end. Yeah. Okay? These are like little brain teasers. Okay? And so you had the answer, right? All that explanation, but you had the right answer originally, right? Okay? That's why, this is one of the reasons why we go through. And this class, any class you take, right, in engineering or science or math or whatever it is, physics, right, we're all going to say, make sure you understand the concepts, okay? Don't just do the problems with the equations, because if you change something, you don't get the concept, then you won't be able to write and derive the new equations, right? Broken record, I'll say the same thing, okay? It's important to have the concepts here. Even if you get it right, try to get a good idea of what is actually happening. Okay. Yeah, so another way, right, to think about this is actually, here's kind of the derivation, okay, of springs in series. Okay. So you can break it into the two deltas, right, and you have the two small forces inside, and then this is going to be the displacement. Because the displacements, they add up, the forces are the same, like we said at the beginning. Okay, but it's the same thing. Delta 2 here, these are equivalent expressions. Okay, so now, right, this is like the simplest one, right? Because now you've seen it twice before. Okay, so what are green, orange, and purple feeling now? What are they feeling? Sure, we'll go over here. Good this time, yes. Yes. Huh? F3, yeah, they're feeling F3, okay? All right, they're all in series with each other, and they're all feeling F3, okay? So you can do it, again, F3 has to be the reaction force on the left side, okay, and then internally, right, and then we can even think, okay, here, maybe we jumped a little bit, but F3, 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 F3 again, they're all F3. Okay. And it's in tension, right? So that means that the delta 3 will be to the right in this case. But we need to figure out the equivalent spring constant here. So it's going to be 1 over k equivalent. This is 1 over k1, this is 1 over k2, this is 1 over k3. Okay? And delta 3 then will be, we're in like that. The overall displacement, like we said at the beginning of the problem, will be the superposition of these. So delta 1 plus delta 2 plus delta 3, right? Where delta 1 is the displacement due to force 1, delta 2 is the displacement due to force 2, delta 3 is the displacement due to force 3. Yeah. Question or comment or friend that walked by? Okay. Good. Okay. Now, if we wanted to ask a different question, that is, what is the elongation? Okay. We did already ask what is the overall displacement, right? But now let's ask a little different question. What is the elongation, or what was the elongation in the middle, the orange one? Well, in this case, was I'm doing.
What time are you finish?
Around 3-ish.
Where's eyesight? How you doing? I just want to say hi for me.
All right. Thank you for your support. Okay. So we have F3 right here on the right, and we have F2 here, and we slice. We're interested in the internal force of the orange member. Once I know that internal force, right, it's constant across the span of that member, then we can say, okay, if I know the internal force, that's what it's experiencing. Okay? And this is maybe, how do you say it? This is a different delta 2, okay, than the one on the previous slide. All right, maybe I should be a little more careful and just say this is the delta orange. Okay. That's what the internal ones experience. That's how much elongation they experience. Is that clear what the difference is here? Okay. So we want to be looking at the internal forces. Okay. Of course, when you now you're going to be like, what? My world is blown, because before I just always thought about the external force on the spring, and that's what I got for the displacement. Since we're dealing with structures, now a lot of times we want to be thinking about what are the internal forces, and they relate, of course, to the external loads, right? But as long as you know what the internal force is across a bar, for example, you can figure out what the overall displacement of that individual member will be, right? So we're saying no change in the spring constant across it and no change in the force across it. Yes?
So what is Fi? Is that the internal force?
That's the internal force, yeah. That's what I'm saying, yeah. Yeah. This is the internal force. Okay? Good. All right. Okay. Yeah, that's a little bit behind. All right, yeah. Okay. And, again, if there's some collab available if you want to use it, that's just that equation, but, you can do whatever you want. Okay, yeah, okay, good. And that's going to be your Q4. And, and Q4 will be the question about the elongation in the middle. So that's how you go about doing that. Okay? Now, we're going to talk about indeterminate axial loading of bars. Now, this is actually a slightly complicated, at least for me it is, a complicated topic. And we're going to do it kind of the more traditional way, and then we're also going to take advantage of the fact that we now have a representation of these bars as springs. Okay? So, first thing to discuss is some vocabulary. Okay? And by the end of the class, you're going to love determinate systems, and you're going to you're going to be welcoming the challenge of indeterminate systems. Okay? So a determinate system is telling us that we just need to do equilibrium, and the number of constraints, okay, is going to be equal to the number of I guess I should say that. The number of equations that you get in the solving for equilibrium is going to be equal to the number of unknowns that you have. Okay? This will become a little bit more clear in a minute, I hope. Okay? But here, this is a problem where we just use equilibrium. We don't need to know anything about deformation, and we can solve for the forces. Okay? So here, we know that the reaction force from the wall is F, and we know that there's no force in the green member, and we can write out what the internal forces are. We don't have to think about displacements. And we'll cover this a little bit more, but this idea of relating forces to displacements is something that in mechanics we call constitutive relationships. It's a fancy word. Okay? And you'll see it come up. When you do multiphysics, if I'm teaching it, we'll talk about it, multiphysics simulations. Okay? If you take DMC, we'll talk about it a little bit, but these are constitutive relationships. So we've kind of introduced K as your first fundamental constitutive relationship, if you want to be fancy and write home about it. Okay? So a determinate system doesn't need anything related to constitutive relationships. An indeterminate system, on the other hand, though, does, and in terms of definitions, it's when we have more unknown reaction forces than non-trivial equilibrium equations. Okay? It's needing, in addition to equilibrium equations, compatibility or constitutive equations. So the compatibility is another way of saying it. Okay? And the compatibility equations involve displacements. The displacements must be compatible with the problem geometry. So now, in a system that's indeterminate, we start to use three pillars. Three pillars are static equilibrium, constitutive relationships, and geometry. Okay, or compatibility relationships if you want, and geometry. So, what do I do to make our first indeterminate system? I put another wall on this side, on the right side. Okay. Now you're like, wait, who cares? How many reaction forces now do I have? Huh? Two, right? I think, yeah. Where are they? There's one.
Like in the other end, and then one's gonna be in the other end.
That's right.
It's gonna be on my side and that side.
That's right. And I have like one equilibrium equation, right? So now I'm up the river or whatever. Okay, I got a problem. Okay. Oh, I need to get up. I need to whatever. I don't know the analogy. So here is the system now written with two reaction forces. And can you see at this point that these reaction forces are not equal to each other either? Okay. Right? They're going in the same direction, okay? But they're likely not equal to each other. So what do? Well, we first will use equilibrium and find our conundrum. We have two unknowns and one equation in equilibrium. Right? So this is a problem. And so it's considered to be indeterminate. Whoops. Okay. Sorry. Okay. So now this is just rewriting things, the same things. Okay. So we have one equation and two unknowns. We need to get to two equations and two unknowns. So what do? We introduce the displacements, okay, and through them we introduce compatibility or constitutive relationships, which is the K, essentially. So one way of writing deformation, okay, which does have to do displacement, but maybe deformation is a better way to write it, is delta C slash A. What does this mean? This means like we're interested in how does C change relative to A? So, in this case, right, we know that we have C relative to A, all right, across the whole thing. And we know that we have B relative to A, right here. We know that we have C relative to B. Okay. And if I know how, even if I remove all these wall barriers, these wall constraints, I have a delta B relative to A, right? I can think of that, okay, if I have, let's say I have B moving to, relative to A moving to the right, okay? And then I have C moving relative to B, right, to the right, that would be the easy case, right? Then that moving to the right plus that moving to the right is going to be equal to, C moving relative to A. Correct? Pretty straightforward. But what is delta C relative to A here in this problem? Now if we think about the whole problem and the constraints involved. It's a classic, right? If you don't know the answer in a math class, guess 0, right? Guess 0, 1, or infinity. Or negative infinity, all right? So 0, it's 0, right? Because they're stuck to the wall. So, yeah, this is just using this in words, okay, but the next thing, okay, is that the delta C relative to A is going to be equal to 0. Okay, so how do we take advantage of this? Well, it'd be nice if we had expressions, right, for these two. Okay, so then we can add them to each other and we know they're going to be equal to 0. And how do we get relationships between C and B, or the displacement of CV and the displacement of VA? what did we just do in the last subsection? Remember we said there's that problem, how do I figure out what the interior element, how do I figure out what that interior element experiences in terms of displacement? Yeah, so you figure out what the internal, you take a slice, you figure out what the internal force is, right? And once I know that internal force, and if I know the stiffness, I can figure out what the displacement is, the deflection is, right? So once again, you slice, and we think, okay, there's some R2 in the green, okay? And I can say that I have a delta CD is equal to minus R2 over K2, right? And the way R2 has been drawn here, we're saying this in compression. Okay? And that makes sense, right? You could have drawn R2 going the other direction, but you know, I've got a force going to the right, so it kind of makes sense that I'm going to put this green region in compression. Okay? And it kind of makes sense that, okay, this region is going to be in tension. Okay? Yes, Isaac?
That's what I was about to ask. So even though we put the R2, we're still not going to add the force. Like, are we going to do the slice with the force in it? Or
Yeah, so we have the slice, right? This is using equilibrium, is R2. I don't know what R2 is, right? But I do know that I can think about the displacement. If I do know R2, right, it's just minus R2 over K2. Just like we did previously. And then delta B, the A, right, this one is going to be related to R1, correct? Okay, so I take a slice, and it's R1. Okay, maybe I should have actually done the slice the other direction. That would have probably been better. Yeah, actually, this is truth. This is a little bit wonky, though, actually. This really should be flipped around. Okay. Yeah. I don't even know how to properly. It's gonna overwrite. But what I prefer is if I had drawn it this way. Okay. Does that look more legit? Okay. And then that R1, right? I can relate that R1. Yeah. Okay. I wrote right over K1 to be that displacement. Okay. Delta dA. Okay. Yes.
I don't understand why R1 and R2 are both like aren't they both equal to F? If you draw like the free body diagram.
Oh yeah. Well, the summation of them is equal to F. Correct. But do you know what they are relative? Like, is one half of F and the other one half of F? Or is one 1/3 F and the other one 2/3 F? We don't know. We don't know what the exact values are. We have one equation. Yes.
I don't quite understand why R1 and R2 are facing the same direction if they're both kind of in the same situation against a wall.
Because I chose. Remember, with the reaction forces, I get to choose. Right? This is not convention time. We're not all going to convention when we're doing external loads, external constraints. This is me picking. I could have drawn them the other way. I could have drawn them any way I wanted. Well, left or right. But I have an intuition, so I want them to be positive. So I drew them this way. Okay? Because if I have a force going this direction, that wall is going to be probably pushing back on the system. And if I've got a force on that, this wall is probably going to be pulling. That's why I drew them that way. Okay? Good. Good questions. All right, so this is just a copy and paste that, and we go to the next slide. And I should make a note. I probably won't fix it for the next time I do this, but this needs to be flipped around. Flipperoonie. Okay? All right, so now we can write out our compatibility equation. Okay, this is the geometry. All right, so I mean, this is really cool actually. This is compatibility or geometry. I mean, you can say geometry. Oh, what did I just do? What did I just do? What in the world did I just do? Okay, that's wild. Cool. All right, go Windows. All right, so that's kind of your, like, you can see that this could be geometric, so this is geometry. Okay, and so I'm using terms loosely. I guess, yeah, usually compatibility refers to geometry, not constitutive. Sorry, I misspoke. And the constitutive relationships refer to, like, this right here. So these are, like, constitutive relationships. Sorry. All right, and then we're using equilibrium. All right, so these are kind of the big three. I didn't know, I was on Wikipedia recently. I didn't know, like, when I thought of the big three, I thought of, like, basketball, but I didn't realize that there was a big three in tennis. There's, like, a big three in, like, a big four. Anyway, never mind. I guess a lot of different sports use these big three, big four, big whatever terms. But in mechanics, our big three are geometry / compatibility, constitutive relationships, and equilibrium. Okay, so anyway, so we do some more algebra, right? So now we plug in these relationships. We now have a relationship. Now we know what the ratio between R2 and R1 is, okay? And we had this equilibrium equation, so now we can plop it in. So now we can figure out what R1 is, and now we can figure out what R2 is. Okay? Okay. And this is cool. This is very cool. Okay? This was not possible in your statics class last semester. Even though you could have drawn this last semester, you would not have been able to solve it. Okay? Because we didn't talk about constitutive relationships last semester. Okay? So this is how you solve, or one approach to solving indeterminate problems in statics. We're going to show you another way to solve indeterminate problems, which is my preferable way. Okay, but this is good. Good way. We just
Well, would it always be equal to 0? Or did we just assume that because it was like against the wall?
What do you mean? What always be equal to 0?
Oh,
the delta CA?
Yeah.
If I've got walls, then yes. Okay? But you could imagine a problem where, like, sometimes Hitler will write a problem, or, people. Actually, there's another spring there. There's a springiness in the wall constraint. Okay? Well, that's actually conducive to this approach too, because then we can say, oh, now I'll just introduce another K term. Okay, I have my spring network. Okay? But yes, that's the idea. Okay, we just talked about superposition a few minutes ago. Okay. Wonderful stuff. We can use superposition with indeterminate problems as well. What do? Well, you take your indeterminate problem and you try to make it a determinate problem, or a couple of determinate problems, we should say. Okay? And so how do you create a determinate problem from an indeterminate problem? You get rid of one of the constraints. Okay? So if I go back to this situation, I remove the right wall, then I've got my determinate problem, which is not the problem I want to solve, okay, but it's an intermediate step. So now I say, oh, I removed the right wall. I can figure out what this system would have displaced had I not put that right wall there. Right? I have the applied force there. I know my K1, I know my K2. Of course, this green member is just along for the ride. Okay, so there's no internal force. The force is in the left member, and the displacement delta 1 there is someone. Huh? F over K1 actually.
Sorry.
Yeah, it's on the left side, right? Good. Thanks, Eric. Okay, so now what do? I say, okay, superposition, right? If I create another force and I add it to the system, right? Then then I can calculate the net or the overall displacement, right? But what I do is I strategically say, oh, the reaction force on the right side of the wall, what does it have to do? It has to apply a displacement that makes the displacement between the left and the right go to 0. So I have to undo what I just did, okay, without that wall there. So I push back, and I push back exactly enough so that it goes back to the 0 position. Okay? And so now what we're saying is this delta 1 minus this delta r, we'll call it because of this FR, that's equal to 0. And delta 1 I know, delta r I also know, right? What is delta r? Delta r, oh, and I guess I should have said, yeah, this is actually, I'm going to little. Okay, all right. So I've got a reaction force. I got rid of that force, right? Remember, we're doing like one force at a time. Okay. So then that's the delta R, okay, associated with the system. And then I can use this relationship. This is essentially my geometric compatibility relationship. And put those together, and we get a relationship for FR. Okay? And once I've got FR, and I've got F, okay, then we've got the ability to use equilibrium, right, to write out what the reaction force on the left side would be as well. Okay? So this is just rewriting things and using equilibrium, and we get that R1 is equal to this, which we got here. Okay? This answer is exactly the same as what we just got from the other technique, okay, using geometric compatibility. Okay? But superposition is kind of fun sometimes, right? And it's not like, you know, I guess if we said use superposition, then you better use superposition on an exam question, but you know, you could do this problem either way. Any questions or thoughts on this? Based on what you know, would you prefer to do the other way, which is fine? Like, what would your preference be? Just like, you've got like 30 seconds of thinking about this. Do you think this idea is easier, or do you think the other idea is easier? This is easier? Okay. Maybe, right? I do. I think it's easier. But sometimes the other technique is what you have to do. You don't always have, I mean, superposition is great, but it may not be the best way to do every single problem. Okay? All right. So, and then if you want, you have Colab that you can use, okay? You can plug it in. Again, it's there for you. It can make your homework easier, but it's up to you, okay? Yeah, right. Okay, and this I need to make sure that I get rid of this in future versions of the slides. Okay. And there's a homework problem, and that's this. Okay, so this is one session. Now we've only got about 30 minutes, if you let me, to go through the next session, all right? So let me go ahead and switch gears. Why don't you take a minute to take a break? I'm gonna also